Okay, so from last time, um, we were talking about the astronaut thing. Uh, so there's the arm. Here's the candidate for astronauty. No! Why did I pick this chair? Yeah, right. It was closest to the coffee maker. Um, yeah, we can calculate what it does. Whoops, that's not. Yes, we would have to do some fluid dynamics, I guess, on that, wouldn't we? Um, we could calculate the force that the cup would apply to the total force the cup would apply to the coffee, and that's not fluid dynamics. Okay, so we have two coordinate systems, this one and one in the middle. And this was parts A and B. And A and B, we got that the acceleration was equal to 0, 0, negative 5 pi squared. And so now we're going to do C, where that coordinate system is fixed to the arm, so it's rotating. It's halfway out. And we're going to use relative motion and rotating coordinate system approach to calculate the acceleration of the astronaut based on that coordinate system at C. How do we expect it to change the acceleration that we calculate? It's a trick question, kind of. Yeah, if it doesn't give the same thing, then this does not work. So what we're trying to do is calculate, use a different perspective, a different coordinate system to calculate an acceleration that we can use in Newton's laws, just like we could with the inertial coordinate system. He's connected to the arm also. So yeah, we'll think about like what you would see if you imagine this is a video camera. Well, what would you see? What would you see? A coordinate system fixed to the arm at C. So what's that video camera going to see as this thing spins around? Well, this one is rotating with the arm, so it's just going to see an unhappy guy the whole time, the whole time around. So according to that camera, if you don't know that camera is moving, somebody observing that camera would look at that and say no acceleration and no velocity. Okay, and then we're going to do the corrections to fix that. So in the coordinate system at C, this coordinate system is fixed to the arm at C. It's non-inertial, and there are two ways that a coordinate system can be non-inertial. The first one is the origin accelerating. Is this origin accelerating? It is, because it's moving in a circle. We're doing the one at C. So the whole thing's rotating around that hinge, and so this is moving in a smaller circle around the hinge. So the origin's accelerating In a circle with a radius, this whole thing had a length of 5 meters. And so the radius of the circular motion of this coordinate system is 2.5 meters. Mm-hmm. In A, it was inertial. And all we had to deal with, that was with the coordinate system fixed. So it just sees the astronaut go around once every 2 pi second. Every 2 seconds. It just sees the astronaut go by. And that's a perfectly inertial coordinate system. Then for B, the coordinate system, its origin was still fixed at that hinge, so the origin wasn't going anywhere. But the orientation was changing, so we had to use rotating coordinate system. No, the origin, right, if it's fixed, it's not accelerating. It also can be moving in a straight line with a constant speed and not be accelerating. That's fine. And the second possibility is that the axes are rotating. Is that happening in this coordinate system? So far you've been wrong about everything. Okay, it is. Good. So yeah, the axes are rotating with the arm, and the arm's changing orientation, so the axes are changing orientation. I mean, you could have the origin fixed at the arm and have it staying at the same orientation as it goes around, you know. But in this case, the idea is that the coordinate system is doing this as it goes around. So yes, the axes complete one revolution every 2 seconds. Okay, so we have both of these. So this is like the deluxe model. You can't get any more non-inertial. So we have to deal with both of these. The accelerating origin, we're going to deal with like this. The acceleration of the astronaut relative to the ground. Is that what we want? Okay, so the acceleration of whatever, in this case the astronaut, with respect to the ground is equal to the acceleration of the astronaut with respect to the origin, plus the acceleration of the origin with respect to the ground. And so we're just going to add on this extra piece, you know, relative motion. So relative motion just says we have to add this on. So how do we calculate the acceleration of the origin relative to the ground? Yeah, so the acceleration of the origin relative to the ground is equal to alpha cross r plus omega cross quantity omega cross r. Alpha is 0. It's moving with a constant angular velocity. What's the r vector? Well, first, what's the definition of the R vector? Because remember, this is going to be a confusing thing going back and forth between R vectors and P vectors. So what's the definition of the R vector? It goes from the center of the circular motion to the point of interest. So in this case, we're going from the center of the circular motion, the hinge, to the origin of our coordinate system, to that point C. So R is 0, 0, 2.5. And what's omega? Zero pi 0, yep. Good job. Okay, so the acceleration of the origin relative to the ground is equal to 0 pi 0 cross quantity 0 pi 0 cross 0, 0, 2.5. And that gives 0, 0, negative 2.5 pi squared. Any questions about that? So that's the acceleration of the origin, and we're just going to add that on at the end. And now we're going to use the rotating coordinate system thing to find the acceleration of the astronaut relative to the origin. So the equation says A is equal to, I'm going to write it as the observed acceleration plus capital omega dot crossed with the position vector plus 2 times capital omega crossed with the observed velocity vector plus capital omega cross quantity capital omega cross p. Here's a question. How come I talk about acceleration as either being the true acceleration or the observed acceleration? And I talk about the velocity as being the observed or the true, but I just talk about position this way. What's the deal there? Is that the true or the observed position? There's only one, and the reason is rotating coordinate systems only cause problems when you take time derivatives. So that position is true, and it's also what you see in the camera. Okay. Yeah, it's always with, so yeah, just whether the coordinate system is rotating doesn't have any effect on the position. And if we were lucky and position was what showed up in Newton's laws instead of acceleration, we'd never have to worry about any of this stuff. But we're unlucky. Acceleration is what shows up in Newton's laws, so we have to worry about these time derivatives. Okay, so let's think about what these things are. So now this camera is mounted halfway down the arm, staring straight at the astronaut the whole time. What does it see as an observed acceleration? 0, yeah. And, okay. Yeah, so before we were thinking in the ground inertial coordinate system and thinking of that arm as a rigid body and doing rigid body motion to calculate the acceleration of that point. And now you're thinking about how quickly the coordinate system's axes are changing their orientation. Yes. Okay. Because the key thing is that those axes, no matter how far out they are on the arm, they're still going through one revolution every 2 seconds. Okay, so same reasoning. What's the observed velocity? 0, yep. And now we just have to think about these things. Oh, well, there's one more thing that goes to 0. It's a constant angular velocity, that arm. So the coordinate system isn't changing angular velocity. So capital Omega, that's how quickly the coordinate system is changing orientation. That's 0, pi, 0. And what's the p vector? Position vector, the position of the astronaut as observed in this rotating video camera. It's halfway down the arm. So 0, 0, 2.5. Radians per second, yep, just like lowercase omega. They're both angular velocities, yep. Because it's a constant angular velocity, this arm, and so it's not changing in time. So the acceleration, I'm going to write these subscripts. So the acceleration of the astronaut relative to the origin all we have left is 0, pi, 0, crossed with the quantity 0, pi, 0, crossed with 0, 0, 2.5. And if you take that cross product, you get 0, 0, negative 2.5 pi squared. And now put it all together with the relative motion. And you get the acceleration of the astronaut relative to the ground is equal to the acceleration of astronaut relative to the origin, 0, 0, negative 2.5 pi squared, plus the acceleration of the origin relative to the ground, which is 0, 0, negative 2.5 pi squared. And you get a total acceleration of 0, 0, negative 5 pi squared, which is what we got in the two other approaches. Cool, right? Any questions about that? So that case, part C is confusing with the accelerating origin and the rotating coordinate systems. I think this example, as we go on with more stuff, this is something you can sort of look back at and sort of see how the different values change and how they add up to come out to be the same thing. Okay, so I mentioned that when I started this topic that there are kind of 3 times that you would need to use rotating coordinate systems, or 3 reasons. The first one is you just can't always choose to put a camera wherever you want. Yeah. affect it. Yeah, well, so say that a camera can tell by the angle that it sees things where things are this way, and say it can see the distance by how the size is changing. Okay. Um, well, if you're trying to track the motion of somebody on a cross-country car trip or something, you're trying to measure like accelerations of someone in a race car or something. All the calculations would be easiest if the camera was mounted on the ground. But if they're going to go 2,000 miles, you'd have to have cameras the whole way to do that. So instead, the only way you're going to be able to do it is to fix a camera in the car, and then from some external thing measure the, GPS or whatever, measure the car's motion. So yeah, that's kind of how a camera measures motion, angles and sizes, and that's an example of where, yeah, it would be nice to have a inertial coordinate system, but you just practically can't do it in that case. Excuse me. Another case is like if you're doing really sensitive calculations, the Earth isn't inertial. Well, so it'd be nice to mount your camera on something inertial in space, but that's not going to work, So you're just going to have to account for the rotation of the Earth. Yeah, I mean, satellites. Well, I mean, the satellites are rotating too, so you have to account for that. Yeah, based on our calculations, it appears. Yeah, I don't know what's an inertial thing, but yeah. Well, uh, I've never done satellite stuff, but they have to account for that in their calculations. That much I do know. Three reasons to use the rotating coordinate system. So the first one is you just don't always get a choice of where your camera is. The second one is you're investigating motions that are easier to describe in a rotating coordinate system. So the specific motion that you're investigating is easier to describe in a rotating coordinate system. An example of that, and the next example I'm going to do is polar, spherical, and cylindrical coordinates. If you think about, well, you probably haven't done a lot of physics with those. In physics 1, did you ever see the thing where if you're using polar coordinates, you get sort of this complicated expression for what a velocity vector looks like and what an acceleration vector looked like? You remember ever seeing that? Act it out? No. Oh, you all had different classes. Okay. Um, so an example of this is polar coordinates. You know, some motions are really easy to describe in polar, and they're really hard to describe in yeah, usually that's what you use it for, right? For helices and yep, cardioids. Yeah. And then the third reason is that the complicated motion, let's say, can be expressed as one simple motion riding another simple motion. The examples that we did with the astronaut fall under the category of number 1. I just specified where the camera was, and we just were like, okay, well, that's what we're limited to. We have to use what that camera sees. So now we're going on to this one, and we're going to talk about polar coordinates. Yes? Okay. Okay. Yeah. No. So if you're trying to calculate the acceleration of a point and your coordinate system is inertial, you're always using the watermelon equation. Okay? Yeah, so the reason we used the watermelon equation was because we were trying to figure out in an inertial coordinate system, what was the acceleration of the origin of our coordinate system. So that's just what we're used to doing, calculating the acceleration of a single point measured in an inertial coordinate system. So that's why that was the watermelon equation. Then we had to use the rotating coordinate system equation because now we were taking measurements in a coordinate system that's not staying in the same orientation and correct it so that you can use it in Newton's laws. Oh, in A? So the first example we did, we just imagined if you had a camera that was facing straight at the astronaut. No, not doing that. If you had a camera that was just facing this way the whole time, okay, that's the camera you'd like to have. Later on, we pretended that we weren't capable of putting that camera in. But the easiest way to do it is just have a camera that's always facing this way. And then every time the astronaut goes by, we can just measure positions and velocities and accelerations. So that's just watermelon equation. Yeah, right. Yeah. Yes, you use rotating coordinate system equation in all 3 of these. But these are the cases that can make it arise that you need to use the rotating coordinate system equation. So let's talk about polar and cylindrical coordinates, probably the rotating coordinate system that you're going to see most often in your career. So I'll start with polar, and then jumping from polar to cylindrical is easy. I'm not going to do spherical because it just gets really messy, but so here's the idea of polar coordinates. So if you think about it, like when you have a rotating coordinate system, you always have there's always the implication of a inertial coordinate system that you're measuring the rotating one against, because you have to know what the rotation is of the rotating coordinate system. In polar coordinates, that sort of implied inertial coordinate system is this. So we just have our x, y fixed there, right? Or really, it just could be x. But anyways, as a particle moves around, so this is the thing that we're measuring. We measure that in terms of 2 values. A distance, r, and a counterclockwise angle from the x-axis, theta. And polar coordinates are r theta. So how far away from the origin, that implied origin you are, and what's the angle from the x-axis. Now here's sort of the weird thing. Those are the polar coordinates, and when we're in a usual orthogonal right-handed coordinate system, you know, x, y, z coordinate system, the coordinates give us a vector. The coordinates are the vector components, right? We've always sort of taken that for granted. Coordinates are just vector components. In polar coordinates, this is not a vector because a vector has to be components in orthogonal directions, you know? So, but in this case, this is not a position vector. In order to define a position vector, we have to choose a coordinate system that's where the axes are 90 degrees apart and it satisfies the cross product requirements. And so our coordinate system that we're going to choose is like this. We'll call this the ER axis, E sub R. So the ER axis always points towards the object that you're tracking. And the E theta axis is perpendicular to that. You know, these are 90 degrees apart. The position vector then is the set of components in the ER E theta directions going to the particle from the origin. Okay, so you can see that this is a rotating coordinate system because as this thing changes its angle, this coordinate system is going to have to turn around so that the ER axis keeps pointing at it. Okay? So we're going to have to use the rotating coordinate system equation. What about, is the origin accelerating? Do we have to deal with that in this case? No, it's staying right here at that fixed point, the origin of that like implied inertial coordinate system. So we're going to track the motion of this ball, this object. Using the fact that the velocity is equal to the time derivatives of the position components plus capital omega cross position vector. And that the acceleration is equal to the second time derivatives of the position components plus omega dot crossed with the position vector plus 2 omega crossed with components dot y. plus omega cross quantity omega cross p. Okay, well, the first thing we have to do is come up with an expression for the position vector. Like, let's just figure out what all these things are. So in terms, if you're just trying to come up with using components in this direction and this direction, you're just trying to express the position of that object. What are the components going to be? How far are you going to go in the ER direction to get to the particle? R, that's right. And then how far are you going to go in the E theta direction? You're already there, good, yeah. So the position vector is just R times ER plus 0 E theta. And I'll, so that we can do cross products and stuff, I'm going to say that there's also a z-axis coming out. So the position vector is equal to R ER plus 0 E theta plus 0, I'll just call it K. And I'm going to write that in the notation that we're used to as R 0 0, where this is the component in the ER direction, E theta direction, and the K direction. For the position, yes. But it's not going to end up being because of these rotating coordinate system equations. Yeah. Okay, so now let's just go through and think about what all these things are. So if this is the components of the position vector, what are the components dot? You know, that just, we don't know what R is, but we're just going to take the time derivatives of each of these components. So you just get R dot 0 0. The position components double dot are just R double dot 0 0. And what else do we need? What's omega? How are we going to represent omega? Well, if you remember that in plane motion, the angular velocity is just the rate of change of the orientation, then omega is just going to be theta dot in the z direction, because it's always rotating about z. Who's with me on that one? Who's still skeptical? Because you said z, but it's rotating. Oh, sure. So this is, okay, good.
Oh, yeah. Kind of like our other guys.
Yeah, right. And then if you take the time derivative of, that's the last thing we need is just capital omega dot. You can just take the time derivatives of those components and you get 0 0 theta double dot. Okay, so let's figure out what the velocity is in polar coordinates. So the velocity is equal to, I wrote them up here, the components dot, which is R dot 0 0, plus omega crossed with the position vector, And so you get r dot 0, 0 plus 0 r theta dot 0. And so the velocity in polar coordinates, a velocity vector, is r dot r theta dot 0. So now if you've ever seen this before, you would probably vaguely recognize that form. Has anyone ever seen that before? No. It would have been just in passing in Physics 1. And then the acceleration is equal to the component's double dot plus omega dot crossed with the position vector plus 2 times omega. Yeah, that's theta. So theta dot is omega. This is omega dot, so this should be theta double dot. Okay. Omega is 0, 0 theta dot. So omega dot is 0, 0 theta double dot. And then 2 times omega crossed with the position dot. So 2 times theta dot crossed with r dot 0, 0 plus omega 0, 0 theta dot cross quantity 0, 0 theta dot crossed with the position vector, which is r 0, 0. And so the acceleration is r dot 0, 0 plus 0 r theta double dot 0 plus 0 2 r dot theta dot 0 plus 0, 0 theta dot crossed with, this one is 0 r theta dot 0 this one comes out to be negative r theta dot squared. It's a vector, so that's in the x direction. So negative r theta dot squared 0, 0. So add those terms all up, and you get the acceleration is equal to r double dot minus r theta dot squared. That's the ER component. The E theta component is r theta double dot plus 2 r dot theta dot and no Z component. So the way it's usually written is r double dot minus r theta dot squared in the ER direction plus r theta double dot plus 2 r dot theta dot in the E theta direction. I saw those equations a lot of times, but I actually never saw them derived that way. So when I figured out you could do it that way, I thought it was really cool. It's not as cool if you haven't seen those equations yet, but someday soon you'll see those in some class, and then you'll say to the person you're working with, like, I could derive those, and then that gives you street cred. Okay, so cylindrical coordinates is basically the same. Let me draw what's going on in cylindrical coordinates. So you imagine a plane where you're dealing with polar coordinates. Let's say so there's your implied inertial coordinate system, x and y components. There's x, there's y. And then there's, instead of being a circle, it's a cylinder. Makes sense. And the z-axis goes this way. And you measure the position of an object. So say you have an axis ER, a perpendicular axis E theta, and your z-axis just stays the same. So that's your z-axis. And an object's position is just, so if this is the object you're tracking, its location is measured as a distance. I can make this better. So it's a distance along ER. And then a distance along the z-axis. Okay. And you derive it exactly the same way. The z-axis doesn't change orientation. And so nothing interesting happens there. And so what you get is the position vector is r, 0, z, ras. The velocity vector is r dot, r theta dot, z dot. That's what it was, right? It's the same as this, but you just have a z dot. And then the acceleration is r double dot minus r theta dot squared the ER component. And then R theta double dot plus 2 R dot theta dot for the E theta component, and then Z double dot. So I'll give you a cylindrical coordinates problem to work on. Yes. I will not be here on Monday, so no class on Monday. And if you're in D-form, no D-form on Monday either. And no office hour. Yeah, exactly. I'll be in Arizona. Yes. They'll be done sooner this time.